Okay, so imagine this. Deep under Hawaii's volcanoes, the familiar ones, something really unexpected's been found.
Yeah, not just lava this time.
No, it's like a hint, a trace of rare metals, and they seem to come from way deeper than we ever thought possible.
Deeper than the mantle, even. It might actually make us rethink how the Earth works.
Seriously. So, this deep dive, we're getting into some fascinating new research. It suggests Earth's core, which we always pictured as this like sealed vault,
Completely locked down, yeah?
might actually be leaking a bit.
Yeah.
And the proof found in rocks, volcanic rocks from Hawaii.
It's pretty wild. The studies from nature, solid source.
Right. So our mission today is to really dig into this. What does finding, gold-like stuff in Hawaiian basalt actually tell us?
And what does it mean if the core isn't this isolated sphere? What are the implications?
Exactly. And why should you, listening right now, find this story from like thousands of kilometers down? Totally fascinating. Okay, let's get into it.
All right, so for ages, the standard picture, scientifically speaking, was that Earth's core is, well, untouchable, pretty
Yeah.
much. A huge ball, mostly iron and nickel. And it holds almost all, like 99.999% of Earth's gold, plus platinum, other
The
metals.
ones that love iron, the ciderphile elements.
Precisely, ciderphile. The idea was these heavy metals sank down when Earth was forming, maybe 4.5 billion years ago.
And got trapped. End of story.
End of story. Just sitting there, locked away.
A kind of planetary Fort Knox, yeah? Can't get in or out naturally. But maybe that picture needs tweaking now.
It looks like it. There's this team led by Nils Messling at Göttingen University. They've been looking really closely at basalt samples, rocks from all over Hawaii, Kauai, the Kilauea Iki Lava Lake.
Okay.
And what they found? Well, it seemed to point to a connection, a direct link to that deep metallic core.
Wow. So what was the smoking gun? What did they actually find in the rocks?
The key thing was finding unexpected amounts of a specific type, an isotope of ruthenium. It's called OURU, ruthenium-100.
Okay, ruthenium. And why is that isotope so special?
Well, this particular one, Irushiru, is strongly connected to the conditions and processes way down deep during planet formation. It's like a fingerprint from the depths.
Huh. And Messling, the lead researcher, he had quite a reaction, didn't he? He said something like,
He did. Paraphrasing a bit, but yeah, he said they realized they had literally strung gold.
huh, nice.
Because it wasn't just that ruthenium was there. It was the amounts
Hmm.
and the specific isotopic signature.
Hmm.
That's what made them think, hang on.
This can't just be from the upper mantle stuff we usually see in volcanoes.
Exactly right. It just didn't fit the profile of the upper mantle alone.
So their analysis pointed where? How deep are we talking?
They concluded this ruthenium-100 must have come from way, way down, near the boundary between the core and the mantle.
The core mantle boundary, that's what, almost 3,000 kilometers deep?
Roughly, yeah. 2,900 kilometers down. A seriously deep origin.
Okay, hold on. How could they possibly trace something from that deep? What was different this time? New tech.
That's the real game changer here. They use these incredibly refined, cutting-edge methods for analyzing isotopes.
Better instruments, basically.
Much better. They could distinguish between isotopes with just tiny, tiny differences. Stuff that was impossible to tell apart before.
Ah, okay, so finer resolution.
Exactly. And that precision let them spot this very specific chemical fingerprint in the Hawaiian rocks. A fingerprint that looks remarkably like,
Like the core's expected composition.
you got it, like the core's signature.
Okay, so they find the signature, but still, how does stuff from the core mantle boundary get all the way up to Hawaii? It's not exactly next door.
Right, good question. This brings us to mantle plumes.
Ah, the giant lava lamps inside the Earth.
Hey, yeah, that's a decent analogy. Think of these massive columns of super hot rock rising up from deep inside the Earth. Very slowly, of course.
Okay.
And when these plumes reach the crust, especially under the ocean, they create volcanic hotspots.
Hawaii?
It's exactly like Hawaii. So the Hawaiian samples are what we call ocean island basalts. They're basically solidified plume material,
Material that's traveled a long way up from the deep mantle.
a very long way, making them perfect candidates to carry signatures from down deep.
So these plumes are like elevators from the depths. And in the Hawaiian rocks, they found higher levels of this specific ruthenium isotope, ARU. Tell me more about that ARU value.
Right, the epsilon 100 ruthenium. What's significant is that it shows an enrichment in something called S-process nuclides.
S-process nuclides. Sounds complicated.
A little, but think of them as specific atomic ingredients cooked up inside stars under very particular conditions.
Okay, star stuff.
Basically, yeah. And this specific stellar signature got locked into Earth's core when the planet was first forming, finding that specific signature in Hawaiian basalt.
Is pretty strong evidence it came from that original deep core material.
Very strong evidence. It connects the surface volcanism directly back to that ancient, deep reservoir.
Wow. There was a quote from Matthias Wilbold, a co-author, right? He put it pretty dramatic.
He did. He said the findings confirm that huge volumes of superheated mantle material, several hundreds of quadrillion metric tons of rock, originate at the core mantle boundary
Quadrillion tons.
and rise to Earth's surface to form ocean islands like Hawaii. And crucially, he added that we now understand these plumes carry actual stuff from the core.
That really does flip the old view on its head, doesn't it? The core isn't sealed.
It certainly challenges it, makes you rethink that whole isolated core idea. So the next obvious question is, how?
Right. How does core material actually get into the mantle plume? What's the mechanism?
Well, the researchers floated a couple of interesting possibilities. Still theories, mind you.
Okay, what are they?
One idea is that maybe an oxygen-rich layer forms in the outer core.
In the liquid outer core.
Yes. And over millions, billions of years, this layer might crystallize. And as it crystallizes, maybe it selectively lets some metals out, like ruthenium and tungsten.
While keeping others trapped inside. Like a selective filter.
Kind of, yeah.
Yeah.
That's one possibility. Another is maybe simpler, just slow diffusion. Elements gradually migrating across the core mantle boundary.
Like osmosis on a planetary scale?
Something like that. Or maybe isotopic equilibration. The boundary zone allows the isotopes to sort of mingle over time.
And does the data, the isotopic evidence, like that ARU value, favor one idea more?
The data strongly supports some kind of core contribution. That specific measurement from Kauai, for instance, 0.17 plus or minus 0.13.
Which sounds tiny, but
But it's significantly different from typical upper mantle values.
Mhm.
That difference is the key. It's like a tag saying, I came from somewhere else. And that somewhere else looks like the core.
it points away from the usual suspects.
Definitely.
And Messling himself said this opens up, what was it? An entirely new perspective.
Yeah, an entirely new perspective on the evolution of the inner dynamics of our home planet. That's a big claim.
It really is. Suggests that Earth's insides are more interactive than we thought.
Absolutely.
Yeah.
It makes you wonder how these core mantle exchanges might have, influenced the chemistry of the surface over Earth's history.
Shaped the continents, the oceans, maybe even the atmosphere over billions of years.
Potentially, yes. It implies the deep Earth might be much more chemically active, more dynamic than our previous models allowed for.
So, wrapping this up then, the huge takeaway is that this long-held picture of the core being totally locked down, totally isolated.
Maybe not the full story.
Right. It's being challenged by actual physical evidence found in, of all places, Hawaiian volcanoes.
It's a fantastic example of how science progresses. You find something unexpected, and it forces you to reconsider fundamental ideas.
Yeah, finding a signature from the core thousands of kilometers down in surface rocks. It's pretty mind-bending when you think about it.
It really connects these vastly different parts of the planet, shows how deep processes can eventually manifest right here on the surface.
So here's a final thought to leave you with. If something as basic as the core being sealed off can be questioned like this, what other impossible things might be happening deep inside Earth that we haven't even imagined yet?
Right. Could this change how we search for mineral deposits, for example, if the core can leak valuable metals?
Or how we understand planets elsewhere? Planets with their own cores? Does this happen on Mars? Venus?
It definitely opens up new questions. It makes you realize there's still so much we don't know about our own planet's inner workings. Lots to think about.